Another technique that can be used for solving systems of equations is called elimination, or it's sometimes referred to as linear combination. But the idea is we're going to add or subtract the equations in such a way to get one of the variables to disappear. So again, just like with substitution, the goal is to move from having two equations with two variables down to one equation with only one variable in it. But instead of isolating one of the variables and then substituting, in this example here, because we have the y's that have the same coefficient, I can subtract these two equations to get those y's to disappear. Since everything in this problem on the left equals the right in both of these equations, if I subtract them, I'm subtracting the same thing from both sides. So on the left here, if I subtract my x's, 3x minus 2x leaves me with just x. 2y minus 2y, those cancel out, so those are just gone. And then on the other side, I've got 8 minus 12, which gives me negative 4. So we can see very quickly we've ended up without the y's present anymore. And in fact, we already know what the x-coordinate of our intersection is. It's negative 4. But that's only half of our answer. We have to find what the second half is. So I'm going to have to substitute that negative 4 value into one of the two original equations. Now, unlike with substitution, I don't benefit from having one of the variables already isolated, so I am going to have a little bit more work on the back end here. But if we go to that top equation, I'll have 3 times negative 4 in place of x plus 2y equals 8. So 3 times negative 4 is negative 12 plus 2y equals 8. If we add 12 to both sides, we're going to get 2y equals 20. So then if we divide both sides by 2, we get y equals 10. So now we've got negative 4, 10 is the intersection point of these two lines. In our last example here, we've got no match between the coefficients of either of the variables. Neither the x's match up nor the y's match up. Neither will substitution be a good option here, because isolating one of those variables is going to leave me with a fraction disaster. So the technique that we have to be able to still use substitution or elimination is to multiply either one or both of the equations so that we'll get a match on one of the coefficients for one of the variables. So our choice is to try to get the x's to match up or the y's, it doesn't matter which. I'm going to choose the y's since they have opposite positive negative signs in my original equations, which means if I get those to be the same but just different by a positive or negative sign, then I'll just be able to add those equations, but ultimately it really doesn't matter. So I am going to multiply this top equation. I have to figure out what do 5 and 3 divide into evenly. So I'm going to multiply the top equation by 3, because 15 is going to be that magic number for me. And then for the bottom equation, I'm going to have to multiply it by 5. So if I do that, that top equation becomes 9x plus 15y equals negative 12. And then the bottom equation, if I multiply everything by 5, is 10x minus 15y equals, and then 5 times 29, well 5 times 30 would be 150, so 5 times 29 is going to be 145. And so now I can go ahead and add these equations since the y's have the same number but just different positive negative signs. So by adding those two equations, the y's will disappear. So I get 19x equals, and then over here we have negative 12 plus 145 is 133. So then our last step is to divide both sides by 19. And so if we need the aid of a calculator, we can use it. But the answer here is going to be 7. So that's our x-coordinate of our intersection. And so now I've got really 4 different places that I could plug that 7 in to figure out what the y-coordinate is. I can use either of these two equations here, but really we're usually best off going back to the originals because the numbers are smaller. So I'm just going to use that top equation for no reason other than it comes first. So I've got 3 times 7 plus 5y equals negative 4. So I've got 21 plus 5y equals negative 4. If we subtract 21 from both sides, 5y equals negative 25, or if we divide both sides by 5, we get y equals negative 5. So here's our intersection point, 7, negative 5. And as always, if we have any doubts as to whether or not we've done this correctly, we can go back, and in this problem or in any of the others, we can plug in those values, 7 and negative 5 for x and y, and verify that that point works in both of the equations. Now, just as we saw in our graphing examples, sometimes we don't just have a single intersection point, but we could have no intersection point where the lines are parallel, or we could have the lines end up on top of each other. Now, without seeing a graph, what does that look like? Well, when we're solving algebraically, whether we're using substitution or elimination, when we go through that process, what we're going to find is both of our variables are going to disappear if we have one of those two special circumstances. The only question is whether we'll be left with a true statement or a false statement, and that'll indicate the difference between having an infinite solution set or no solution. So if we take a look at this first example here, I'm going to use elimination. I'm going to go ahead and multiply this top equation by 3 to get the x's to match up, but we can see that's also going to mean the y's are going to match up. So I'm going to get 9x plus 6y equals 12. And so now if I subtract these two equations, you can see the x's are going to disappear, so those are gone. The y's are going to disappear as well, so we get 0 over here on this left-hand side. But on the other side, we get 3 minus 12, which is negative 9. And that is decidedly not true. 0 does not equal negative 9. So in a circumstance like this, where all of our variables disappear, but we end up with a false statement like this, then we know that these lines are parallel and that there is no solution to this system. So we also learned that this system is inconsistent, meaning that there is no solution to that system. In the second example, so here we're set up for substitution. We've got y by itself in the second equation, so I'm going to drop that in here. So I've got x minus 5, and then in parentheses I'm going to put that 1/5 x plus 2 equals negative 10. So I'm going to distribute that negative 5, so negative 5 times 1/5 is negative 1, so I've got negative x, negative 5 times 2 is negative 10, equals negative 10. And so now when I gather my like terms here on the left, the x's are going to subtract out, and so this time our variables disappear just like they did on the previous example, but we're left with a true statement instead of a false statement. Negative 10 does equal negative 10, 0 does not equal negative 9. And so what this tells us is that these two lines are the same. They represent the same line. They are on top of each other. But remember, we are not going to put all real numbers in this circumstance. We're instead going to use that format that communicates that it's all of the points that are on the line. So that's going to be x comma y, and then we can write down either of the two equations, since again they're representing the same thing. So I'll just use that top one, x minus 5y equals negative 10. And so this is our solution. So the system is consistent because we do have an answer, but we say that it's dependent because the two equations represent the same line.